while the boards are drying, I'm just going to start on the side. So hopefully this is, I know it's a little bit of a stretch for the front row, but it's either that or wait. All right, so we've had sort of 4 quite mathematical lectures, and not that there's going to be no maths in this one, but I thought it would be quite a good time to just sort of take some time out from all of this differential geometry and discuss a little bit about physical solutions. So you will have already met black holes in the introductory course. Probably, did you do just Schwarzschild, or did you just Schwarzschild? Okay. So what I want to do is to kind of go back and look in more detail at black hole solutions. I want to talk about why we believe there are black holes. So I'll give you a sort of analytic toy argument, which is indicative of the existence of the Chandrasekhar limit. Then we'll look at, if you remember, I talked about cosmological constant solutions. We'll look a little bit at those. I'll tell you how you get the Penrose diagrams, because usually when we talk about black holes, we sketch these diagrams on a piece of paper, and those diagrams represent the causal structure. So again, I believe you did Kruskal coordinates. Yeah, so I'm probably going to go through that quite fast, because Kruskals are like the main step on the way to drawing a Penrose diagram. And then if I've got time at the end, and I hope I have, I'm going to talk about a Euclidean black hole solution. So let's take a closer look at our spherically symmetric static solution. So this is what we derived yesterday. As a sort of total mass inside radius r. Now, of course, as I said, you have to be a little bit careful about that, because there isn't really a local, unambiguous definition of energy in GR. But I'm imagining here that we have a static solution of some sort of object. So we're thinking of looking at a star, and we're approximating it as being static. So this, if you like, is intuitively mass inside right. So yep.
The argument of M is that a different R, like is also integrating over R, right?
Yeah, I'm always very lazy with the way I write down integrals. I'm never very precise by making it an R prime in my integram, because it's, So if we now, this arose from the naught Einstein. So now let me look at the RR. Now, I talked about the radial Einstein equation in terms of the vacuum solution yesterday, but now I want to do it just in general, for a general source. So you'd have to go back to yesterday's lecture to just check, input in the Ricci components to just double check this Einstein equation. So when we were doing the vacuum solution, this m was just a constant, okay? But now I'm saying, let's just imagine we're trying to solve for a star. how do we go about doing that? So in addition to the naught naught and R Einstein equation, we've obviously got the theta theta, but instead of using that, I'm going to use conservation of energy momentum, just because it's a bit more convenient. So this is saying that the divergence of the energy momentum tensor vanishes. So I'm now going to take a perfect fluid for my energy momentum tensor, which isn't a bad approximation. It's quite common in cosmology for sure. And I'm going to take that it's isotropic. So what that means is perhaps a little bit more of a stretch. But it's saying that PR, at least, properly normalized, the pressures in the radial and angular directions are the same. So if I look at the radial component of this equation, then you can sort of see that's going to give me the gradient of this radial pressure in terms of some connection components and the other components of TAB. Right, so this is what I get when I write it down in longhand. I've got two connection pieces because T has two indices. And I find, sure enough, if I now just call PR as just P because I've got a single pressure, so I put in all the various connection components, and I find that, there's sort of an obvious cancellation of the radial, the RR sum there and the RR piece over here. But in addition, I've got a rho term coming from naught naught here, and then the theta theta and phi phi pieces, which are those there. So what I end up with is an equation for the gradient of the pressure in terms of the time component of the metric. So whereas this equation here gives me the gradient of the time component of the metric in terms of the pressure. So you can kind of see now that I've got my m of r, which is an integral of rho, and then I've got some other pair of equations which are first order, which tell me about the remaining potential in the metric and my pressure. So now I want to just talk about solving those equations, and the reason why I chose this particular simple format. So this sort of process was developed by Tolman, Oppenheimer, and Volkov, and they were obviously trying to look at a general relativistic star. So I'm going to just show you what this looks like. Obviously a real star is messy, and you couldn't do it on a blackboard. You have to integrate it numerically. But I think what's remarkable is that we can, by making a couple of very simple and not physically unreasonable assumptions, we can write down an analytic solution which gives us genuine physical information about what happens with, proper general relativistic stars. It really does sort of mimic what the star does. So we're going to model the star by a top hat. Potential. So what that means is I'm going to take rho to be some constant density inside the star and 0 outside the star. Obviously an idealization, but not an unreasonable one. So this tells me my M function inside the star is just the sort of naive mass coming from that constant density profile. And outside the star, it's simply M. Because we have to go to the Schwarzschild solution outside the star. Yep. Sorry?
Even if we had a real star, then such a thing, I mean, what would change? What would change? I mean,
well, we would probably imagine that the star would get denser as we moved into the center. Simply, yeah, I mean, that's why I say it's a bit idealized, but it's not that bad, you know, in the sense that I think that the less dense the star is, the better an approximation this is, because it's kind of, you imagine it getting denser because of its self-gravity. So
we'd still have this kind of time-like boundary where it sort of cuts off it.
Yeah, so we would imagine with a more realistic star that we would have a definite cutoff, or fairly, I mean, a relatively short scale cutoff, where we would go from being, you know, some definite density to essentially 0 density. So we would expect that. I mean, this is, of course, because I'm really talking about a very simple model, perfect fluid, I'm not really imagining that, you know, like this is a real star which is actually letting out light, okay? So it's not really a star, it's a brown dwarf or something, I don't know. Right, so for the pressure, then we're going to solve our pressure equation. So we sort of input what our A primed on A is, and we can see that this is, you know, sort of coupled differential equation, but you know, it really is just an equation for P. And then it's going to be, wait a minute, let me just. Okay, so we obviously want our pressure to go to 0 at the edge of the star, and in here, this is sort of inputting the expression for A prime just directly from the equation, and then from here to here, I've inputted that M of R. So that's why you see the 2gm going to an 8 pi g rho naught there, and then just tidied the expression up a little bit. So because we've chosen such a simple density function, we can actually solve this. Though it's one of those things that you sort of think, oh yeah, you know, how on earth did they come up with that? Okay, so I'm simply stating, I'm writing down that. You can check, if you like, that it is indeed a solution for that pressure gradient. It satisfies our requirement that the pressure vanishes at the edge of the star. And if we look at P of 0, so let's ask what's the pressure in the center of the star. So the thing that you notice is there's lots of these 2gm on Rs floating around here. So this is the pressure at the center of our sort of simple star, but there's a sort of interesting feature of it. If we look at the top line, or we look at so the top line is negative and the bottom line is negative. I suppose I should have written it the other way around. You can kind of see that, that the denominator is actually going to hit 0 or potentially it could hit 0, depending on the value of Gm and R. All right, don't think that was a very clear statement. So this is the central pressure of the star. If I imagine either sort of increasing the radius or sort of changing the amount of matter in the star, changing the density, in such a way that we drop the radius of our star down to 9 GM on 4, then this central pressure becomes infinite. Now, actually, we should probably worry before it becomes infinite. We should start worrying once it gets to be the same order of magnitude as the local energy density, in fact. But let's just say this is where we start to worry. Beyond this point, we will hit an infinite pressure before we get to the center of the star. So what this is indicating is that if we have a given massive star, then we can't squeeze it too much. So we cannot squeeze one of these solutions inside a radius, well, in this case, with these assumptions, a radius of 9 GM on 4, so just over 2 GM. So there's lots to criticize about this, of course. It's very simple. It's a toy model, but it's a toy example which illustrates the Chandrasekhar limit. So the Chandrasekhar limit is a limit on the mass that a self-gravitating object can have before it produces a black hole. Now, of course, Chandrasekhar did it properly. He thought about interactions, took into account, this notion that you could, in fact, have nuclear fusion, et cetera, et cetera. So it's a much more sophisticated argument. But this very simple analytic argument that you can just pop on a couple of boards is actually sort of giving insight into some real physics here. This is something that really does happen. We try and push too much matter together. We can delay the inevitable, as in the way very large stars delay the inevitable by producing light, but in the end, it will form a black hole or else, I guess, explode. Right, so now that we've sort of got to the point where we say that at some mass, we've got to have one of these Schwarzschild or Schwarzschild-like solutions. Let's now look at actually characterizing the causal structure of a black hole. So the causal structure of a black hole, we usually encode in a pictorial form, and that's the Penrose diagram. So I'm going to derive in detail the Penrose diagram for the Schwarzschild black hole, because that's the simplest one, but you can basically do it for any space-time with horizons. The key is, when you've got one of these horizons, one of these coordinate singularities, you find a way to extend across the horizon by going to locally null coordinates and then kind of rescaling them in a way you've already seen with the Kruskal coordinates, which allows you to step across the horizon and extend the space-time inside. So here we're just going to do it. Simple case, one horizon, very simple metric. Okay, so this is the Schwarzschild metric, and as you've already seen, we can extend the Schwarzschild metric across R equals 2gm to what we call the maximally extended Schwarzschild using Kruskals. So the first thing you do, as you've already seen, no doubt, is you define a new radial coordinate such that your metric has the light rays in your new radial coordinate are at t is plus or minus r star. So it's like looking for a null system. So just for convenience, I'm not going to keep my 2 GMs. I'm going to encode them as r plus, the location of the event horizon. So the Kruskals are null coordinates which make the t and r star, your old time and radial coordinates, non-singular by exponentiating. So the problem that you have at the black hole event horizon in the standard coordinates is that time runs off, coordinate time runs off to infinity on the event horizon. So if you exponentiate it in a clever way, then you can kind of get rid of that infinity, or you can sort of make it less problematic. So if I now look at what the sort of TR part of the metric is, the null part of the metric, du dv, well, obviously du is sort of minus 1 and 2r plus u times d of t minus r star. So I get minus uv over r plus squared, 4r plus squared, sorry. So I get, you can see that we've already starting to build the Schwarzschild looking piece. And then if I look at what uv is, well, if I multiply u by v, I get an minus r plus squared. These t's cancel in the exponent, and I just end up with r star on r plus. But now if I look at R star, my tortoise coordinate has the R piece, and then it has a logarithmic piece. So when I exponentiate it, this has been engineered so that when I exponentiate it, I get 1 minus 2gm on R. So I get my Schwarzschild metric times some function which is entirely non-singular. It's just e to the r and r plus. The only problem that you could see, possibly, is when r goes to 0, and that's okay because that's where you expect trouble. So if I then look and just sort of try and pick out features, so features of this are that if r is constant, uv is constant. If t is constant, then u1v is constant. For R plus, well, UV has this factor of R minus R plus over R plus in it. So this allows me to identify the sort of key features of my black hole spacetime, my Schwarzschild spacetime. So if I sketch it in UV coordinates, and just conventionally we draw the UV coordinates of 45 degrees because they're light lines, they represent null rays. Then if I look at where r is 0, UV is positive, so it's in this quadrant here, and it's a hyperboloid. And a t equals constant line is just u proportional to v, and r equals constant is, again, a hyperboloid. So this is our maximally extended Schwarzschild, and should be just sort of revision. So now I'm going to define new coordinates . Because what I'd like to do is to be able to give a sort of finite little picture representing the black hole, and while the Kruskal diagram tells you about the causal structure of the black hole, it's open-ended. It's still an infinite drawing. So what I want to do is I want to now squeeze down my picture. I'm going to shrink this infinite range down to a finite range in both v and u. And I do that just by taking the inverse tangent, arctangent. So in this case, v equals 0 corresponds to p is 0, v is r plus, corresponds to p is pi on 4, and then I use the tan formula, multiple tan formula, to identify where my singularity is. So uv equals r plus squared, which was, of course, r equals 0, corresponds to p plus q tends to infinity, so P plus, sorry, the tangent tends to infinity, so P plus Q is plus or minus pi on 2. So if I now draw again in PQ space, so here's we're still dealing with null coordinates, so here's my P, and here's my Q, then P plus Q equals pi on 2 is this line. It's now a straight line in PQ space. So this is the point pi on 2. And then here we've got P is pi on 2, Q is minus pi on 2. So these are the boundaries, the sort of limit. So V is, we're sort of looking at our limiting, we sort of shrunk infinity down to pi on 2. And so now what I've got is I've got this maximally extended Kruskal diagram, and I've shrunk it down into a finite box. So this is the Penrose diagram. And of course it was also developed by Brandon Carter, so sometimes you see it called Penrose-Carter diagram. But usually, I guess we say Penrose diagram because we're lazy. Right, so that's the Schwarzschild solution done in detail. And just want to talk about some other causal structures. We could do the same trick with Minkowski space. In fact, it's a lot easier with Minkowski space. Because what we do here is we say U is T minus R, V is T plus R. We've got null coordinates which are completely well defined, cover the space. The fact that R is positive tells us that V minus U is positive. And so if I sketch my UV plane, it means that we're in the right-hand half of the plane. And so here this would be saying that tan P is greater than tan Q. And so what I end up with in my PQ coordinates is just a little triangle. So this is my P, my Q, and so that's Minkowski space. So I just label what these things are. We usually give names to some of these boundaries. Now that we've drawn our space-time in the finite box, so to speak, we can identify different regions. So if we go to the future along a light ray, we get to what we call future null infinity. And similarly, this one here is past null infinity. And we denote those by a curly I, which we call scry. So this is just a useful terminology. Here in the middle, we've got an I naught, down here I minus, up there I plus. And so I plus is future, time like infinity. I minus is the past one. And I naught is space-like infinity. So you sometimes think of these things as being points because that's what they look like in what we've drawn. But don't forget we've suppressed extra dimensions here. We've got a 4-dimensional space-time, and we've drawn it on a blackboard. So we've suppressed the theta and phi. So around every point on the Penrose diagram, there's a sphere. So just remember that. You know, they're very useful for telling you about causal structure or encoding it, but don't be too literal with them. Remember, there's more information than what you see. So now let's move on a little bit and talk about other examples of space-times. So an important one is the de Sitter metric. Now, I already talked about that when I was writing down solutions to that spherically symmetric metric when I just put in a cosmological constant. So if you remember, I said that the solution was, we still have the 2gm on R for a simple solution. It still solves the equations of motion, but the cosmological constant has the effect of adding an R squared in the potential. So if we ask about horizons, then this potential, the Newtonian potential, A squared, tends to 0 at, well, roughly close to 2gm. Obviously, I'm assuming L squared is large here, and roughly L. So we get 2 horizons for the de Sitter solution here with a black hole mass. So the first one is obviously a black hole horizon, and the second one is what we call a cosmological event horizon. So the thing about the cosmological horizon is it's there whether or not we've got a mass. So it stays there. So if I think about what my Penrose diagram is, well, if we think about the black hole part of it, for small r, let's assume L is quite big. For small r, this piece is essentially irrelevant. And what we've got looks like the Schwarzschild solution. So I can say that for small r, I have something looking like this. So I expect this to be my R less than roughly 2gm piece. Now for large r, or as r starts getting bigger, this piece now becomes irrelevant. And what I've got is another 0 of A, but kind of now looking where A goes, so where R goes towards L. So it's an event horizon. It's got to be like. So if I go from here, I'm increasing R. So remember, my R equals constant lines look roughly like hyperboloids. So I'm moving out. Where can I put another 45-degree line? Well, it's got to be here. It's the only other thing I can do. So this is, if you like, I mean, it's not exactly 2gm, but it's close to 2gm. And this is roughly at L. So that's the cosmological horizon. So I maximally extend across, and then on the other side, sort of very, very large R, I don't really expect any singularity at all, and so that means I've got to be able to go sort of as far as I can in R. Now, these are not the best, these are sort of actually pretty rubbish coordinates to talk about large R, but in fact what you see if you do de Sitter in different coordinates is that you get this structure where you truncate, this is really sort of not T, but future infinity. And then, amusingly, just as you get 2 copies in Schwarzschild, de Sitter, you actually have, in the maximally extended space, a whole infinite sequence of copies of the same space-time.
So this is not sensitive to having just static coordinate patch de Sitter, or?
So in the cosmological event, yes, the cosmological event horizon is precisely, and it's precisely because you've chosen silly coordinates for de Sitter, right? So I was just about to write down a few other coordinate systems for de Sitter. The reason why, or, you know, I say it's silly, it's only silly if there's no black hole. It's a totally sensible thing to do if you have a black hole, because you want to be able to describe your black hole in a nice way. So let me just write down the other coordinate systems of de Sitter, and then just remind me to come back and I'll make a couple of comments about which one to use and when. So, perfect timing there to say that de Sitter has many coordinate, or many, well, obviously any manifold has many coordinate systems, but de Sitter has many sort of neat slicings. So let me call them nice coordinate systems. And this is really an indicator of the high degree of symmetry that the manifold has. So let me just write down the sort of three that are the most useful. So here we are with the one we've just used, the static patch. The other two you come across when you do cosmology, or mostly in cosmology, one of which is the global patch, which means that there are no coordinate singularities, and the whole of de Sitter spacetime is covered by these coordinates. So this here is a three-sphere, all right? And the other common one that you'll see, again, in the context of cosmology, I'll call it flat inflation, because that's really where you see it, as the inflationary universe. So the question I had was, you know, why was this cosmological horizon just because I'd chosen the coordinates? And the answer is absolutely yes, because you can see there's no singularity in the global system. Now, the flat this flat system, you can see that as t goes to minus infinity, you've got this, there's a sort of question about what's actually going on here, because this prefactor goes to 0. But so it doesn't, this flat patch does not cover the whole of de Sitter spacetime. So one of the nice things about de Sitter space is that you can actually represent it. It has a lovely geometrical picture by drawing a surface in 5 dimensions, a 4-dimensional surface in 5-dimensional space-time. So you have a hyperboloid, t squared minus x squared minus y squared minus z squared minus w squared equals minus L squared, and so this is your t. And of course the R5 is just flat R5. So if you take we'll be talking about this, you know, in later lectures, but if you take this four-dimensional surface, this hypersurface in five-dimensional flat space-time, and then you look at the metric on this hyperboloid, which it inherits, you know, simply by projecting down the five-dimensional metric onto the hyperboloid, that is exactly the de Sitter metric. So that is the sort of, and then you start to see, I suppose I should have checked what the static patch was, but obviously you can see where the global patch comes from. You simply take your S3 around your hyperboloid, there's your S3, and then this time coordinate is just, this t here is just that tau there. And then the flat one is simply taking, it's a bit like conic sections really, sort of taking a slice across at a diagonal, and you take the upper half of the hyperboloid. So that's kind of how it works. Now, the other very interesting space-time, actually, is anti-de Sitter space-time. And so we get anti-de Sitter space-time when we take lambda to be negative. So we simply swap the sign. Lambda is -3 on L squared. So in this case, again, I can tell you what my potential is, because we wrote it down. All we've done is swap the sign of the cosmological constant. And so we get the same potential, but now instead of -r squared on L squared, we've got +r squared on L squared. So what that means is that there is no cosmological type event horizon. Our metric is just fine at large R. So an interesting feature about this is that I could say, where did that one come from and do I need it? Okay? So if I track back where the one came from, the one came from essentially the sort of, if I looked at where I calculated the curvature, there was a sort of 1/c² piece. And the 1/c² piece is basically coming from the two-sphere. So we've got a two-sphere in our geometry, and that has an intrinsic curvature, which is giving me a 1/c², which is plugging into the Einstein equations and giving me that one there. So I, in fact, in anti-de Sitter space, I don't need to have spherical black holes. So if I now write my metric, I'm going to use the fact that I know B is 1/A. And this is now just some two-dimensional space labeled by a kappa. And if kappa is 1, then I've got an S2, which is what I've already discussed in a lot of detail. If kappa is 0, I just have R2. If kappa is -1, I've got an H2, or a hyperbolic space-time, two-dimensional hyperbolic space-time, negatively curved. Then the Einstein equations are solved by kappa -2gm on R minus λ/3r². So this is a sort of example of a Birkhoff-type theorem, and you can prove it quite generally in arbitrary dimensions for arbitrary cosmological constant, or something analogous to this. So you can see that in flat space, no lambda, or de Sitter space, positive lambda, you absolutely have to have kappa equals 1 for a squared to be positive and for t, therefore, to be time-like. In anti-de Sitter space, this piece over here is now positive. So at large R, you've always got a positive Newtonian potential, and therefore you don't have the need for kappa to be 1. So anti-de Sitter space has different black holes. So I suppose a hole is a bad word then, because a hole suggests something localized. So they can be planar and hyperbolic, as well as spherical. So the other key is you only have one horizon. So for example, R plus is 2gm L squared to the 1/3 if kappa is 0. And your Penrose diagram now looks like that. So it is quite different. And this is just indicative that actually anti-de Sitter space is really quite a different kettle of fish. So you're probably going to be seeing more of anti-de Sitter black holes. I might either talk about them again or we may construct a tutorial around them. But you know, there's actually some quite interesting things that happen in anti-de Sitter space with black holes, particularly black hole thermodynamics. So just to wrap up now, I just want to give a very preliminary sort of commentary on things to do with thermodynamics. And so in order to do this, I'm going to do something which, if you haven't seen it before, will look very strange. I want to think about a black hole solution, or it's not really a black hole because it's not causal, but I want to think about the Schwarzschild solution, but instead of being a real sort of physical space-time, I'm going to imagine it's just a sort of standard Riemannian manifold. In other words, it's Euclidean, it's plus, 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 the signature. So my Euclidean Schwarzschild looks like this. I just make it plus, 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 plus. It's still going to be Ricci flat, because it was Ricci flat in the Lorentzian case. And the only thing that changes with Euclidean metrics is you see a sprinkling of minus signs sort of throughout your calculation. But it doesn't change the essence or the terms that actually crop up. So this is a standard Riemannian manifold. It's obviously not flat because we've got these potentials here. So what does it look like? Well, obviously we've got to worry about what happens as R goes to 2gm. Now, whereas in the Lorentzian Schwarzschild solution, we could imagine going beyond 2gm because we could see that if R went less than 2gm, it just looked as if T and R, the coordinates, were swapping roles on the other side of the event horizon. Trouble with this is, if we try to go to R less than 2gm, we're going to change the signature. Not good, okay? So we need to stop at 2gm. So this should be a boundary to the manifold. And because we want a non-singular manifold, we are going to demand that it is not singular. Okay, so that's setting out what my aims are. Let me now see if I can achieve that. Right, so let's look at what happens. Obviously, away from 2GM, there's nothing the matter with this. So as R tends to 2GM, we've got R minus 2GM over R d tau squared plus 1 over R minus 2GM dr squared. So the obvious thing to do is to say that if we look at a new coordinate, rho, which is proportional to the square root of R minus 2GM, then when I take d rho squared, I'm going to have something that looks like dr squared over R minus 2GM. So here I've got 2 rho d rho is lambda dr. So d rho squared is dr squared, lambda squared dr squared, over 4 rho squared, over 4 lambda R minus 2GM. So I have correctly identified what looks singular at R equals 2GM. So if I now set lambda equals 4 times 2GM, then that is correctly, at least to leading order, that is going to exactly mimic the radial part of the metric. So now I've got to look at what happens with the dt squared piece. So R minus 2GM is rho squared on lambda. So that's rho squared on 8GM. And then I've also got 1 over R, which is 1 over 2GM. So again, we're looking just to leading order. So what I've got here is rho squared over 16g squared, m squared. So my metric looks like rho squared d of tau over 4gm squared plus d rho squared. So leading order. So if I were to identify tau over 4gm with, suppose I shouldn't use theta, should I? Let me use it chi, another angle. Then this looks like the origin in polar coordinates. So that's non-singular. But what it requires is a periodicity. So it requires that chi plus 2 pi is identified with chi. So if I translate that back, chi is tau over 4gm. So that tells me that tau plus 8 pi gm has to be identified with tau. So my space-time has a periodic Euclidean time and is regular at 2gm. So if I look now at large r, at large r, g tau tau goes to 1. So I've got a cylinder at large r. Okay, so this is my tau coordinate. Here's r, and I'm just suppressing theta and phi. So at large r, I've got a cylinder. But as I come down to small r, I've got to have something non-singular. And so what I get here, so this is 2gm, which is just like the origin in polar coordinates. So we sometimes call this a black hole cigar. And that is what a Euclidean black hole looks like. So why on earth did people do this? Well, in fact, if you want to do field theory at finite temperature, what you do is Wick rotate to Euclidean time and then make your Euclidean time periodic. So what we've actually done here is said that we've Wick rotated to Euclidean time, but we now haven't chosen to make time periodic. We've been forced to make time periodic. And so what this is indicating is that the black hole has a temperature, and the temperature is given by the inverse of the periodicity of Euclidean time. Less than a minute. So in field theory, so the temperature of a black hole, then, is 1 over 8 pi gm in, according to this, if I reinstitute all the constants that I have set to 1, then this is what we get for the temperature of a black hole. Now, you should be rightly skeptical based on this argument that this really tells you that black holes radiate. In order to check that black holes radiate, you really should do field theory on the Schwarzschild space-time. So, of course, that was what Stephen Hawking did in the early 70s, and indeed he showed that the correct transformation between the in-state and the out-state looked like a thermal state of that temperature, precisely that temperature. And it was only later on in the 70s when he and Gary Gibbons were starting to look at Euclidean formulations and a Euclidean path integral approach that they sort of spotted this very nice relation. So we'll come back to this when we follow in their footsteps in a way and talk about a Euclidean approach to looking at black holes. But this is kind of a very simple calculation that you can do to see that black holes can radiate. And in fact, if anybody ever needs, or if I need to calculate the temperature of a black hole, this is what I always do. It's the easiest way to do it. Okay, better stop, otherwise they'll come and start cleaning me rather than the boards.